The sky has never been empty. For decades, it only looked that way. High above the cloud line, beyond the reach of weather and wings, objects have been moving with a precision that defies instinct. Not drifting, not falling, not orbiting. Moving with intent. Silent, controlled, unapologetically fast. Now, the data is no longer hidden in fragments. It has been released. And it changes the scale of the question. Because what was once dismissed as misidentification now carries measurable velocity, recorded acceleration, and trajectories that ignore the limits imposed by human engineering. These objects do not glide through air as aircraft do. They cut through it. They do not obey inertia in ways we recognize. They stop without deceleration. They turn without banking. They accelerate without visible propulsion. The numbers are not subtle, speeds exceeding thousands of miles per hour with no thermal signature of combustion. Maneuvers generating forces that would crush any known material, let alone a human body. Transitions between air and water without loss of velocity, as if the boundary between two physical mediums simply does not matter. There is no sonic boom, no plume, no wings, only motion. And motion in physics is never random. It obeys laws, it follows energy, it leaves traces. That is what makes this different. Because the new data is not a story. It is not testimony. It is instrumentation. Multiple sensors, independent systems, radar returns locked across platforms, infrared signatures that do not match known propulsion, optical tracking that confirms shape, movement, and consistency. A pattern begins to emerge, and patterns demand explanation. At the core of the problem lies a contradiction. Every object with mass resists acceleration. Every change in direction requires force. Every force requires energy. And energy, when used in large quantities, leaves a signature: heat, radiation, exhaust, disturbance. These objects rewrite that expectation. They behave as if inertia is optional, as if mass can be decoupled from motion, as if the air itself offers no resistance. To understand why this matters, one must consider the limits of current aerospace design. The most advanced aircraft on Earth operate within a narrow envelope defined by material strength, aerodynamic drag, and pilot survivability. Even unmanned systems, freed from the constraints of human physiology, remain bound by energy density and thermal management. Nothing we have built can perform what has now been recorded. And yet, something is performing it. Not once, not rarely, repeatedly. There are moments captured in the data where an object hovers motionless against hurricane-force winds, then accelerates to hypersonic speed in less than a second. No gradual build, no ramp, just an instantaneous transition from stillness to velocity. In classical mechanics, that is a problem. In engineering, it is impossible, unless the rules being applied are not the ones we assume. This is where the weight of the release settles in, because the question is no longer whether unidentified aerial phenomena exist. That question has been resolved by observation. The question now is what framework of physics allows such behavior to occur? And that is a far more unsettling question. If the data is accurate, then either our understanding of motion is incomplete, or these objects are using principles not yet mastered by human technology. Concepts that have been theorized at the edges of physics begin to feel less abstract. Manipulation of space-time, control over gravitational interaction, inertial dampening not as fiction, but as a necessity to explain survival under extreme acceleration. The sky, once a domain of predictable forces, becomes something else entirely. A testing ground, a boundary, or perhaps a threshold. Because the most disturbing element is not the speed. It is the control. Speed can be chaotic, explosive, destructive. Control implies intelligence. Every recorded maneuver suggests precision, deliberate changes in vector, sustained tracking of moving targets, responses that indicate awareness of surrounding objects. This is not debris. This is not weather. This is not random noise in a sensor array. This is behavior. And behavior forces a confrontation with possibility. The release of this data does not answer the question of origin. It does not assign intent. It does not declare presence or purpose. What it does is remove the illusion of certainty. For the first time, the unknown is not an absence of data. It is a presence within it. And that changes everything. What has been released is not a revelation of answers. It is a revelation of measurements. And measurements are where reality becomes unavoidable. Velocity, acceleration, cross-domain movement. Radar cross-sections that appear, vanish, and reappear without continuity. Infrared signatures that refuse to behave like heat should behave. Each data point is small in isolation, almost trivial. But together, they form a structure that cannot be ignored. Like stars assembling into a constellation that was always there, waiting for the eye to connect them. To understand the depth of this shift, one must begin with the most fundamental principle of motion: inertia. Inertia is the quiet law that governs everything that moves. It is the resistance of matter to change. A spacecraft coasting through the vacuum continues forward because nothing stops it. A jet turning in the sky leans into the curve because its mass resists the change in direction. Inertia is not visible, but it is always present, like gravity's silent partner. Now imagine an object that behaves as if inertia has been reduced or removed, not lessened gradually, but bypassed entirely. An object that can move from 0 to thousands of miles per hour without experiencing the crushing force that such acceleration would normally impose. In human terms, the body would collapse under the stress. In material terms, structures would fracture, heat would build, and failure would cascade in milliseconds. But the data shows continuity. No breakup, no disintegration, no thermal bloom, just motion. This leads to a possibility that sits at the edge of theoretical physics. If inertia can be manipulated, then motion itself becomes a different kind of process. Instead of pushing an object through space, space could be adjusted around the object. The difference is subtle in words, but profound in consequence. Pushing requires force. Adjusting space requires control over the geometry of reality. In Einstein's description of the universe, gravity is not a force in the traditional sense. It is curvature. Mass bends space-time, and objects follow that curvature. Planets do not orbit because they are pulled by invisible strings. They fall along the shape of space itself. Now consider a technology or a phenomenon that can locally alter that curvature. Instead of accelerating through space, it reshapes the path it occupies. The effect would look exactly like what is being observed. Instant acceleration without force. Sharp turns without stress. Motion that appears disconnected from energy expenditure, because the energy is not being used to move the object in the conventional way. It is being used to redefine the path the object occupies. If that is even partially true, then what is being recorded is not advanced flight. It is a different category of physics in operation. And yet, the data does not stop at motion through air. There are events where objects descend from high altitude into the ocean without slowing down. No splash, no plume, no explosion of displaced water. The transition between air and liquid appears seamless, as if the density of the medium is irrelevant. To appreciate how extreme this is, consider the difference between air and water. Water is roughly 800 times denser than air. Entering it at high speed is equivalent to impacting a solid surface. Even the most advanced projectiles cannot transition between these environments without losing energy, creating shock waves and generating immense heat. But these objects do not behave like projectiles. They behave as if the concept of resistance is optional. As if drag, one of the most persistent forces in fluid dynamics, can be minimized or bypassed entirely. Drag is not just a nuisance. It is a fundamental limit. It is the reason aircraft have shapes that taper and curve. It is the reason re-entry vehicles glow as they fall back to Earth. Drag converts motion into heat. It is the universe's way of reminding moving objects that energy must be accounted for. When drag disappears, so does a major constraint on movement. And when constraints disappear, new possibilities emerge. But those possibilities carry weight, because if an object can ignore drag, then it is not interacting with the medium in the way we expect. It may not be pushing against air or water at all. It may be altering the conditions of interaction at a boundary we do not yet understand. This leads to another anomaly present in the data: the absence of expected signatures. High-speed objects generate heat. Friction with air compresses molecules, raising temperature to extreme levels. This heat is easily detectable in infrared. It is one of the most reliable ways to track fast-moving systems. But these objects often lack that signature. They move at hypersonic speeds, yet appear cold, or at least not hot in the way they should be. This contradiction is not minor. It challenges the direct relationship between velocity and thermal output, a relationship that has been confirmed in every known high-speed system. If velocity is present, but heat is not, then something is interrupting the mechanism that converts motion into temperature. Again, the implication is not just advanced engineering. It is altered interaction with physical law. The deeper one looks, the more the data begins to resemble a mirror held up to our own assumptions. We assume that movement requires force. We assume that force produces heat. We assume that transitions between environments create turbulence. We assume that energy leaves traces. These assumptions are not arbitrary. They are built on centuries of observation, experimentation, and mathematical consistency. But they are still assumptions. And assumptions, when confronted with contradictory evidence, do not break reality. They break our understanding of it. There is a philosophical weight to this realization. Humanity has always defined itself by the boundaries it understands. The horizon was once an edge. The sky was once unreachable. Space was once an abstraction. Each time a boundary was crossed, the definition of what is possible expanded, and with it, the definition of what we are. Now, the boundary is not geographic. It is conceptual. If objects exist that operate beyond our current understanding of motion, then the universe is not just larger than we thought. It is deeper, more layered, more complex in ways that are not immediately visible. This introduces a subtle but profound shift in perspective. The unknown is no longer distant. It is active, present, interacting with the same physical space we occupy. Not in a dramatic or overt way, but in a measured, almost clinical manner. Observed through sensors, captured in data streams, quietly recorded as anomalies until the anomalies form a pattern too consistent to dismiss. And within that pattern lies a question that is difficult to ignore. If these objects are not bound by the same constraints, then what anchors them to our environment? Why here? Why within the atmosphere, where interaction is inevitable? Why not remain in the vast openness of space, where emotion is easier, where resistance is minimal, where observation is more difficult? Their presence in controlled airspace, near naval operations, within regions dense with human technology, suggests something more than coincidence. It suggests proximity with purpose, not necessarily intent as we define it, but direction, trajectory, awareness. And awareness, even in its most basic form, implies a relationship with surroundings. The data does not confirm that relationship in a human sense. It does not indicate communication, hostility, or cooperation. What it shows is consistency, repeated appearances in similar contexts, movements that align with points of interest, moments where the objects seem to react, adjust, or maintain distance relative to other moving systems. This behavior exists on a spectrum between passive observation and active engagement. And that spectrum is where interpretation becomes unavoidable. From a purely physical standpoint, the existence of such objects forces a re-evaluation of technological limits. From a philosophical standpoint, it forces a re-evaluation of position. Because for centuries, humanity has occupied a central role in its own narrative. Not geographically, but intellectually. The builders of machines, the decoders of nature, the observers who transform mystery into knowledge. But what happens when observation reveals something that operates beyond the observer's current framework? The role shifts from author to audience, from controller to witness. And that shift is not comfortable. It introduces uncertainty at a level that is difficult to quantify. Not fear in the traditional sense, but a kind of cognitive gravity. A pull toward questions that do not yet have stable answers. A recognition that the map of understanding has edges, and those edges are closer than we believed. Yet, within that discomfort lies something else. Possibility. Because every expansion of knowledge begins with an anomaly, a deviation from expectation, a result that does not fit. The orbit of Mercury did not align with Newtonian predictions, and from that discrepancy emerged general relativity. The behavior of light at small scales defied classical models, and from that tension emerged quantum mechanics. Each time, the universe presented a contradiction, and each time, the contradiction was not an error. It was a doorway. The current data may represent a similar threshold, not proof of a specific origin, not confirmation of a narrative, but a pressure point in our understanding of physics. A signal that the current model, while powerful, may be incomplete. And if it is incomplete, then the implications extend far beyond unidentified objects in the sky. They reach into propulsion, energy, materials, and the fundamental nature of space and time. They suggest that the limitations we consider absolute may, under certain conditions, be negotiable. And that idea is both exhilarating and deeply unsettling, because limits provide stability. They define what can be built, what can be predicted, what can be controlled. Remove or alter those limits, and the structure of expectation begins to shift. What was once impossible becomes uncertain. What was once certain becomes questionable. And in that transition, the familiar world becomes slightly less solid. Not because reality has changed, but because our grip on its rules has loosened. The data does not demand belief. It demands attention. It demands that each anomaly be examined, not as an isolated curiosity, but as part of a larger system of behavior that is yet to be fully understood. And most importantly, it demands humility, because the universe has always been under no obligation to conform to human expectation. It simply is. Vast, layered, indifferent to assumption, and now, through a collection of measured, recorded, undeniable events, it has offered a glimpse of something operating within it that does not fit the patterns we have spent centuries refining. Not a conclusion, not an answer, but a fracture in certainty. And through that fracture, a deeper reality begins to show. What the instruments recorded next pushes the problem from physics into information. Sensors do not just measure motion, they encode states. They translate photons, radio echoes, and thermal gradients into integers and waveforms. In those translations, structure appears. Patterns within noise, repeats within randomness, signatures that point to systems rather than accidents. The newly released datasets are dense with such structure, recurrent waveforms, synchronized detections across platforms, and timing correlations that behave like clocks. Consider timing. In electronics and in nature, timing is language. Pulses arrive with intervals that encode sequence. A beating heart, a pulsar's steady tick, a radar's cadence. Each is an ordering principle. In the UAP data, there are intervals and phase relationships that persist across observations. The return echoes align with no random distribution. They display coherence. Coherence implies design, or at least consistent process. It suggests that whatever is generating these signatures is not a transient artifact, but a system with stable dynamics. Now translate that to information theory. Information requires capacity, encoding, and error control. Communication across noisy channels demands redundancy and structure. Biological systems, human-made systems, theoretical constructs, each organizes information to survive, to act, to adapt. If the observed phenomena exhibit structured timing and cross-sensor coherence, then we are witnessing information processing at work, not merely passive motion. This moves the inquiry from how fast something can move to how it perceives, measures, and perhaps even reasons about its surroundings. The presence of structured signals near areas of intense human activity, aircraft carriers, radar arrays, and surveillance lanes, hints at interaction with our technological environment. The recorded behavior is not only about locomotion, it is about situational awareness. These objects appear to sense where we are, how we move, and they respond with patterns that imply detection and selection. Selection is a primitive form of agency. To select is to differentiate. To differentiate is to prioritize. If patterns persist that align with our sensors' blind spots, or if approaches vary depending on platform posture, then the system behind these phenomena may possess a model, however rudimentary, of its environment. Models require memory and processing. Memory demands a substrate. Processing demands energy. Here, the data is again confounding. Energy consumption usually leaves a footprint: heat, emissions, disturbances in electromagnetic spectra. Yet, persistent traces of operation remain faint or absent. It is as if computations are being performed in a manner that does not fit the typical energy-to-signal mapping we expect. This raises two possibilities. Either the energy is being expended in a channel we are not monitoring, or computation itself is occurring through mechanisms that couple differently to measured spectra. Both possibilities are unsettling in different ways. If energy is being radiated in forms we cannot yet detect, then our instruments are blind in a way that matters. If computation can occur with significantly lower observable expenditure, then our assumptions about energy efficiency and the limits of information processing may need revision. The consequences cascade into fields as diverse as computing, materials science, and surveillance. Beyond information and energy, the spatial behavior of these objects reveals another layer of perplexity. Stealth, not as concealment, but as selective presence. They appear in proximity to sensors, yet manage to confound identification. They generate returns while simultaneously evading classification. This is not the simple trick of absence, it is nuanced. A feature may be visible on one band, invisible on another. It may appear in radar as a coherent blip while remaining optically ambiguous. Such selective manifestation indicates a control over how the system couples to observational modalities. Think of it like tuning a radio. The same broadcast can be loud on one frequency and silent on another. If these objects can tune their observable profile, they possess a form of interface with the physics of detection. That interface could be passive, material properties that naturally interact with certain wavelengths, or active, deliberate modulation of emissions and reflections. Either way, the implications are profound. It would mean that observation is not simply an act performed by us upon the world, but a dialogue in which some systems can choose how, when, and on what terms they are observed. The philosophical resonance of that idea is substantial. Observation has been the foundation of scientific authority. We measure, we infer, we build models. If systems can selectively modulate their visibility, then the act of observation becomes contingent. The observer's power diminishes. Certainty erodes into negotiation. The epistemological bedrock shifts from absolute description to relational description. What we know depends not only on the world, but on the terms under which the world allows itself to be known. This is not merely an abstract problem for philosophers. It would alter how intelligence is defined, how security is structured, how science is practiced. Laboratories would need to account for systems that can control observability. Surveillance architectures would need to assume adversaries, or simply entities, with the capability to choose their perceptibility. The legal and ethical frameworks that govern observation, privacy, and national security would all be strained by the possibility that certain actors can regulate whether they are seen. Layered onto information and observability is morphology, form and structure as inferable from sensor fusion. The released datasets include optical frames, radar silhouettes, and multispectral readings that, when combined, suggest a variety of geometries. Some returns are spheroidal, others are oblong, some are flat and featureless. The lack of a consistent aerodynamic profile across events is telling. Aerodynamic shapes emerge from design pressures, efficiency, lift, stability. When shapes vary widely and yet produce similar anomalous dynamics, the inference is that shape may be secondary to function. The underlying mechanism of motion might not rely on shape-driven interaction with fluids. Instead, shape could be a byproduct of other constraints: thermal management, sensor placement, structural support, or even an incidental consequence of a medium-transcending propulsion method. Consider the analogy of a submarine and a satellite. Each moves through different domains with designs optimized for those domains. An object that refuses to be optimized for either domain, yet operates effectively in both, suggests a decoupling of movement from medium. That decoupling undermines the taxonomy of vehicles and their operational envelopes. if movement can be abstracted away from interaction with air or water. Then our categories collapse and must be rebuilt around principles other than fluid mechanics. This has cascading technological implications. Energy storage, materials, control systems, all the subsystems that define engineering programs would need rethinking. If inertial effects can be mitigated, then structural requirements change. If drag is irrelevant, thermal design changes. If observability can be modulated, then passive stealth becomes conceptually different. Industries from aviation to deep-sea exploration, from satellite deployment to micro-robotics, would encounter foundational questions about feasibility and design. Philosophically, these technological consequences are a mirror of a deeper human unease: contingency. Civilizations build on assumptions that feel universal. The sun rises, gravity holds, machines obey cause and effect. Anomalies in those assumptions expose contingency. The way of things is not necessarily the only way. That realization can be destabilizing. It dissolves the comforting sense that the rules humans have discovered are the rules of the universe in totality. Ontological humility becomes necessary. If the universe supports behaviors outside our paradigms, then human knowledge is provisional in a very literal sense. Not wrong, simply incomplete. This should not be an occasion for despair, but for methodological recalibration. Science advanced because past thinkers accepted anomaly and pursued it. The discovery of a phenomenon that does not fit a model is an opportunity to expand the model, even if that expansion requires radical theoretical invention. But radical invention carries social consequences. Knowledge is power, and power rearranges social orders. If the technologies implied by these observations were to be harnessed, the strategic landscape would change. The ability to operate without clear signatures, to traverse domains unimpeded, to process information in ways that evade detection. These capabilities would be as valuable as they are disruptive. Concentration of such capabilities, should it occur, would reshape geopolitics, economics, and the ethics of deployment. Returning to the observational records, another unsettling pattern emerges: persistence. These encounters are not singular events in a forgotten past. They are ongoing. The data set spans years, geographies, and contexts. Recurrence implies a sustained phenomenon, not a transient anomaly. Persistent systems require maintenance, oversight, or autonomy. If autonomous, they possess resilience, the capacity to continue operating without external intervention. Resilience suggests robustness in design and possibly purpose. Purpose is a fraught word when applied to systems we do not understand. It carries teleology, intent, a narrative. Yet purpose can also be neutral, operational, functional, maintaining orbit, sampling environments, minimizing exposure. The recorded persistence invites us to ask, what is being achieved by this ongoing presence? Is it surveillance, study, resource extraction, testing, or something else beyond our categories? Our curiosity pulls at that thread, but the data resists clear answers. It yields patterns without narratives, structure without declared motive. That gap between empirical pattern and narrative closure is philosophically valuable. It forces restraint. The human mind seeks story. It wants to fill blank space with causality and meaning. But science advances when narrative impatience bows to evidentiary patience. The data sets demand a disciplined approach. Develop hypotheses, test predictions, refrain from premature synthesis. In historical terms, this is familiar. The pattern of comets once evoked omens until methodical observation reduced them to orbital mechanics. The difference here is scale and implication. The phenomena interact with the instruments of modernity and challenge theoretical frameworks that underpin much of our technology. Finally, the socio-technical implications are unavoidable. Information about these observations is distributed unevenly. Release of data has been partial, controlled, and contested. That unevenness interacts with public perception, media dynamics, and political narratives. The choice of what to disclose, when, and how shapes social reaction. Transparency becomes an ethical variable. Withholding fosters suspicion. Premature disclosure invites speculation. The new data sets force institutions into difficult positions. How to balance national security, scientific integrity, and public right to know when the subject matter unsettles foundational assumptions. The philosophical horizon here is one of responsibility. If we inhabit a world where certain systems operate beyond familiar constraints, then the duty of inquiry extends beyond curiosity. It becomes an obligation to expand our understanding carefully and collaboratively. It requires openness to revising basic principles and humility in the face of anomaly. It also requires vigilance about how new knowledge is governed and deployed. In sum, the data moves us from questions about objects to questions about cognition, information, and the architecture of observation itself. It asks not only what moves and how, but who perceives, who decides, and on what terms knowledge is shared. Those are not only scientific questions, they are moral and political ones, and they invite reflection on how a species built on observation responds when the act of observation becomes reciprocal. The patterns in the data begin to trace not just behavior, but capability. Capability is the aggregate of effect. What a system can do within its environment. It is revealed in margins, in the extremes, in the points where ordinary machines fail and these objects persist. To grasp the technical magnitude of what has been recorded, it helps to ground the discussion in concrete scales. Consider acceleration. Modern fighter jets can pull 8, 9, sometimes more Gs in controlled turns for short durations. Those maneuvers require titanium, advanced composites, and pilots trained and sometimes chemically assisted to withstand the forces. Even unmanned vehicles are limited by structural integrity and the heat generated by rapid acceleration. The recorded events show changes in velocity and direction that, if calculated with conventional mass assumptions, would imply accelerative forces orders of magnitude beyond what those materials can survive. Structures should disintegrate. Electronics should fail. Any life inside would be vaporized. Yet, we see coherent objects. Solid returns on radar, continuous optical frames, and no evidence of catastrophic failure. Translate that into engineering terms. Either the objects have mass far lower than assumed, making acceleration less damaging, or they possess structural or inertial mitigation far beyond our current technology. The first possibility, extremely low mass, would create other anomalies, such as negligible radar cross-section or different interaction with atmospheric drag. The second possibility implies active control over inertial frames, an ability to decouple mass from acceleration. That capability would be revolutionary. It would change payload calculus, launch physics, and safety constraints of travel. Now consider energy. The energy required to accelerate a mass to high-speed scales with a square velocity. Hypersonic transitions imply enormous energy expenditures if done conventionally. The absence of commensurate thermal signatures suggests that either energy is being funneled into non-thermal channels, or that the objects employ mechanisms of motion that circumvent conventional kinetic energy accounting. If energy is being channeled into altering space-time geometry locally, the bookkeeping of energy looks different than in Newtonian mechanics. Energy may still be expended, but the manifestations, heat, sound, shock waves, would be redistributed or suppressed by the process that enables the motion. This touches on conservation laws, which are foundational to physics. Conservation of energy and momentum are not suggestions. They are empirically robust principles with deep theoretical grounding. Any new mechanism that appears to sidestep the familiar manifestations of these laws must be reconciled with them at a deeper level. Either the laws hold in a broader framework with different observable consequences, or our application of them in these contexts misses critical elements. Hidden reservoirs, coupling to degrees of freedom outside our detection, or local modifications to the metrics that define energy and momentum. Moving from energy to control, there is the matter of maneuverability. Among the observed features are instantaneous angular shifts, reversals of vector, and prolonged hovering in turbulent conditions. For a craft to perform such maneuvers, control authority, the capacity to alter forces acting on it, must be extraordinary. In human technology, control is exerted through thrusters, control surfaces, reaction wheels, or vectored thrust. Each requires interaction with a medium or the ejection of mass. The lack of observable reaction mass casts doubt on those mechanisms being in play. Imagine steering without shedding a reaction mass, like turning a car by rearranging the road beneath it rather than turning the wheels. That metaphor captures the strangeness of the recorded dynamics. If the environment can be locally modulated to guide motion, then the craft is not merely subject to forces. It is actively reconfiguring the scaffolding of motion itself. The implications ripple outward. Navigation becomes a problem of geometry rather than thrust. Precision becomes a matter of field modulation rather than actuator fidelity. Then there is the question of endurance and autonomy. Some encounters show repeated returns to the same region, temporal patterns that suggest scheduling or periodicity. Persistence implies either the capacity for autonomous operation over extended periods or a logistical network that supports repeated deployment. Autonomy at scale requires reliable energy sources, self-repair mechanisms, or a low-energy mode of existence that minimizes degradation. If the observed systems operate with near invisibility and low waste signatures, their power budgets and maintenance cycles would defy current engineering models. Materials science also emerges as a central puzzle. Surfaces appear to withstand thermal and mechanical stresses that would erode known alloys and composites. There is little evidence of ablative damage, pitting, or surface fouling after extreme maneuvers. That suggests either active thermal management, redirecting heat away from vulnerable regions, or fundamentally different physical properties. Materials that interact with fields to reduce effective stress, or that reconfigure at the molecular level in response to forces, would require fabrication techniques and chemistries beyond present capabilities. From these technical considerations arise practical hypotheticals with profound consequences. Consider transportation. If inertia can be mitigated, travel across planetary scales becomes less constrained by fuel and structural mass. If drag can be reduced or nullified, atmospheric flight could match the energy efficiency of orbital coasting. These are not incremental improvements. They are discontinuities. Economies built on transport costs, supply chain limitations, and material constraints would be reorganized. The political geography of access, what places are remote or connected, would shift dramatically. Economics is one domain affected. Warfare is another. The ability to maneuver with impunity relative to existing sensor and interceptor networks alters deterrence paradigms. Speed without signature circumvents early warning systems. Stealth that is selective undermines current classification of visibility. Nations would face asymmetric risk profiles. A technologically superior but static defense is vulnerable to an adversary that masters these new modes of movement. The strategic calculus of defense, offense, and escalation would need re-examination under conditions where traditional correlations of signature, intent, and capability no longer hold. Beyond statecraft, there is the matter of knowledge distribution. If such capabilities exist and are concentrated in private or governmental hands, the asymmetry of access could widen existing power differentials. The ethical responsibility of sharing transformative knowledge becomes urgent and fraught. Historical precedents, nuclear technology, biotechnological advances teach that diffusion is complex, often contested, and rarely equitable. Philosophically, the presence of systems with such capability forces a reconsideration of human exceptionalism. The Enlightenment project built confidence around rational models and technical mastery. Confronted with phenomena that operate outside those models, the narrative of mastery is interrupted. This is not merely metaphysical discomfort, it affects identity. Societies that derive meaning from technological ascendancy may need to reframe narratives about humankind's place in the order of complexity. That reframing can be liberating or destabilizing, depending on cultural resilience. There is also an epistemic lesson about modeling and prediction. Our models are powerful because they compress reality into tractable rules. But compression sacrifices detail at the margins. When anomalies accumulate at those margins, the compression fails. The response is twofold. Improve observation, more bandwidth, broader spectra, denser sensor networks, and broaden theory, accepting that new variables may be required. This dual approach is methodologically straightforward but operationally demanding. It requires investment, international cooperation, and an institutional humility that is politically scarce. Ethically, the emergence of phenomena that challenge existing moral frameworks invites questions about response. How should humanity proceed when faced with technologies or behaviors that could be exploited or misunderstood? Do we prioritize defensive postures, collaborative scientific inquiry, or cautious secrecy? Each choice carries moral weight. Secrecy can keep populations safe in the short term, but erodes democratic trust. Openness can accelerate scientific progress, but risks panic or misuse. The balance is delicate and the stakes high. Finally, there is a metaphysical dimension. The nature of agency. The recorded precision and recurrence suggest agency, but agency need not equal intention as humans experience it. Agency can be algorithmic, emergent, or systemic. A weather pattern that consistently returns to a path does not intend in a human sense. It follows dynamics. Yet humans instinctively ascribe purpose to regularity. The philosophical task is to distinguish between behaviors that imply sentience and those that imply robust systemic dynamics. That distinction matters morally and practically. It informs whether we treat the phenomena as subjects deserving ethical consideration or as systems to be measured and controlled. In sum, the capabilities inferred from the data touch on engineering, geopolitics, economics, ethics, and identity. They force a cascade of reappraisal of what machines can do, of how societies organize knowledge and power, and of how humans understand their own place amid systems that may surpass familiar constraints. The question is no longer only, what are these objects? It becomes, how will we, as a species, respond to the realization that our models of the possible have been outgrown? That is the heavy question the data imposes. Technical, existential, and ultimately democratic in its demand for a collective answer. Data, once released, becomes a conversation with the world. It is an invitation to test, to replicate, to probe. The fifth block must therefore follow the path from observation to experiment, from pattern to hypothesis, and from hypothesis to the practical programs that would either confirm revolutionary physics or dissolve anomalies into known phenomena. This is the domain where laboratory discipline meets strategic urgency. First, consider the imperative of verification. Scientific method demands reproducibility. An observation recorded by one sensor must be corroborated by others, under controlled conditions. The released datasets already show multi-sensor corroboration in many cases. Radar tracks aligned with optical frames and infrared bursts. But the next step is intentional replication. That means designing experiments that can elicit similar behaviors under monitored conditions. It means establishing sensor arrays with complementary modalities, synchronized timing, and open data pipelines so correlations cannot be dismissed as artifact. The analogy is simple. If the sky offers intermittent notes of a new melody, we must build an orchestra of instruments tuned to catch its full score. Building that orchestra requires technical breadth. Radar networks must expand frequency coverage, from VHF through millimeter bands, with waveform diversity to prevent blind spots created by adversarial or unknown coupling mechanisms. Optical systems need high frame rate, high dynamic range cameras synchronized precisely with inertial measurement units and spectrometers to capture not just shape but material signatures. Infrared arrays must span short-wave to long-wave bands, calibrated to detect anomalous thermal gradients. LiDAR and sonar in littoral zones should be integrated to study air-water transitions. Magnetometers, gravimeters, and space-based platforms can add dimensions that ground-based systems cannot. The technical challenge is to create a mesh of sensing that cross-validates each channel, exposing any selective observability the phenomena might exploit. Parallel to sensor deployment, data science protocols must be rigorous. Raw data must be preserved in immutable formats with provenance metadata. Analysis pipelines should be transparent and reproducible. Machine learning can assist in pattern recognition, but models must be interpretable. Black boxes will only deepen controversy. Statistical thresholds for anomaly must be conservative to avoid false positives and generous enough to detect weak signals. The analogy here is forensic. A crime scene yields traces that only make sense when contextualized, time-stamped, and compared across independent observers. The stakes, potential revision of physics, demand forensic discipline. Experimentation must also include controlled stimuli. If the phenomena show sensitivity to electromagnetic emissions, to radar sweeps, or to active tracking, then structured probing, varying power, frequency, waveform, and posture, can reveal response characteristics. Such probes must be ethical and cautious. They might provoke reactions that are benign, instructive, or risky. The scientific principle, however, is clear. Passive observation is often insufficient. Carefully designed interaction yields insight. Think of it as the difference between eavesdropping and conversation. To learn, one must sometimes speak and observe the reply. Institutional design matters as much as instrumentation. The interdisciplinary nature of the problem, physics, materials science, information theory, aerospace engineering, and philosophy, demands collaborative structures that cross traditional silos. Single-agency approaches risk both blind spots and politicization. A distributed, international consortium of academic institutions, open laboratories, and vetted government participation could provide the balance between security and scientific openness. Transparency serves credibility. Secrecy serves short-term control, but long-term distrust. Building trust is as technical as building telescopes because it determines whether data sets will be shared, peer-reviewed, and challenged. Funding and resource allocation are practical hurdles. High-bandwidth sensor networks, space-based platforms, and long-duration sea trials require substantial investment. The argument for such investment rests on potential returns that are both defensive and generative. Defensively, understanding anomalous phenomena preserves situational awareness and national security. Generatively, the technologies and scientific understanding that emerge could catalyze industries, propulsion, energy, materials, that transform economies. The policy question is not solely about cost. It is about strategic prioritization. Allocate resources now to learn or risk being surprised later. Ethical frameworks must be developed in parallel. Experiments that probe unknown capabilities may have unintended consequences. They may create disturbances in local environments or trigger responses by the very systems being observed. Ethical oversight should include risk assessment not only for human participants, but for ecological systems and for geopolitical stability. Open ethical review boards, including philosophers, ethicists, and public representatives, can help mediate the tension between necessary experimentation and the precautionary principle. The analogy is medical trials. Potential benefits are balanced against risks, and transparency in protocols builds public legitimacy. Communication strategy is equally crucial. The release of partial data sets has already produced waves of speculation. Future disclosures should be accompanied by clear, accessible explanations of methods, uncertainties, and what remains unknown. Scientific humility should be communicated without apology, emphasizing the iterative nature of discovery. This approach reduces the vacuum that rumor and sensationalism exploit. It also invites public participation. Citizen science networks, amateur astronomers, and hobbyist radio operators can meaningfully augment formal observations if given tools and guidance. Beyond observation and experimentation lies technological translation. What a confirmed understanding would enable. If mechanisms that mitigate inertia or modulate observability are validated, the translational path must be managed responsibly. Technologies that transform mobility and detectability have dual-use character. They can enable exploration and rescue or asymmetric military advantage. International norms and perhaps treaties may be necessary to govern development and deployment. Historical parallels exist in arms control and in space law. Those frameworks offer starting points, but will likely require expansion to address modalities that alter foundational constraints like propulsion and stealth. Philosophically, the process of investigation illuminates how knowledge grows. The methodical, cautious approach described here is an exercise in collective epistemic virtue. It recognizes that extraordinary claims require extraordinary rigor, and that extraordinary rigor is social as well as technical. The virtues of openness, reproducibility, and interdisciplinary exchange are not abstract ideals. They are practical necessities when the object of study can confound single-discipline analysis. There is also a moral imperative tied to the potential scope of transformation. If understanding these phenomena yields technologies that can alleviate human suffering, more efficient transport, cheaper energy, better disaster response, then the case for equitable dissemination strengthens. Conversely, if the technologies exacerbate inequality or concentrate power, then the failure of governance will be as consequential as any technical failure. The investigation, therefore, cannot be separated from policy that aims for global benefit. Finally, the psychological and cultural dimensions of the investigation must be acknowledged. Societies receiving repeated signals that their models are incomplete will experience cultural oscillations, curiosity, fear, fascination, and resistance. Education systems should prepare citizens to engage with uncertainty, to understand probabilistic reasoning, and to interpret scientific claims critically. Media literacy, scientific literacy, and public engagement become part of the experimental program, not peripheral, but central. The experiment is not only on the phenomenon, it is on ourselves, our capacity to respond thoughtfully rather than reactively. In operational terms, a roadmap could include immediate steps. Deploy targeted sensor arrays in regions of frequent activity, establish international data repositories, fund interdisciplinary research centers, and mid-term steps. Launch space-based observatories, develop standardized protocols for active probing, and negotiate transparency agreements. Long-term, the program could pivot toward applied research contingent on confirmatory findings, with governance structures in place to manage dual-use risks. Each of these actions presupposes a choice: to treat the data as an epistemic emergency demanding coordinated, transparent inquiry, or to treat it as an operationally sensitive curiosity to be managed in secrecy. The first path is arduous, politically complex, and vulnerable to missteps, but it builds a durable foundation for knowledge. The second path may deliver short-term control, but risks long-term fragmentation, suspicion, and missed opportunity. The scientific imperative is clear. Anomalies must be pursued with rigor, openness, and ethical care. The strategic imperative is equally clear. Ignorance at scale is dangerous. The moral imperative ties them together. Knowledge that could reshape the human condition should be sought not for hoarding power, but for collective understanding and stewardship. This is the experimental and institutional horizon the released data demands. Investigation is no longer optional. It is a duty to the science that seeks truth, to the polity that must manage consequences, and to the future that will inherit any discoveries we make or fail to make. The way we choose to proceed will imprint on the next century as decisively as any technology born of prior revolutions. The final shape of this story is not a revelation about objects in the sky. It is a revelation about us. Because every measurement, every anomaly, every contradiction has slowly redirected the lens inward. The data did not simply expose something external. It exposed the boundaries of our own understanding, the quiet assumptions we mistook for universal truths. For centuries, humanity has lived inside a framework of predictability. Gravity pulls, matter resists, energy leaves traces, motion obeys rules that can be written, solved, and trusted. These principles allowed us to build aircraft that cross oceans, satellites that map the planet, and instruments that read the faint radiation of the early universe. We learn to trust the consistency of reality. But trust in science is always provisional. And now, that provisional nature is impossible to ignore. Because what has been observed is not just a technological anomaly. It is a philosophical fracture, a reminder that the laws we understand are not the limits of existence, only the limits of our current comprehension. Imagine standing on a shoreline at night, looking out across a vast black ocean. For most of history, that horizon represented the unknown. Dangerous, infinite, unknowable. Then ships were built, navigation improved. The ocean became a pathway, mapped and measured. But now imagine that, just beyond that familiar horizon, something begins to move. Not waves, not storms, but structures. Patterns that do not behave like water. Motions that do not follow tides. You realize that what you thought was an ocean may only be the surface of something deeper. That is where we stand. The sky is no longer just atmosphere. It is a boundary layer of a deeper system we are only beginning to perceive. The implications extend far beyond physics. They reach into identity. Humanity has long defined itself as the observer, the analyzer, the species that transforms mystery into knowledge. This role has shaped culture, philosophy, and even morality. To understand is to control. To measure is to master. But what happens when understanding lags behind observation? When we can measure something precisely, yet cannot explain it? The role shifts. We are no longer solely the interpreters of reality. We become participants within it, observers who are also being observed, not necessarily with intention, but through interaction. Our sensors detect, but they are also detected. Our presence is not invisible. It leaves signatures, electromagnetic emissions, heat, movement. In a universe where detection is reciprocal, observation becomes a relationship, not a one-way act. This realization carries a quiet humility. It dissolves the illusion of isolation. For a long time, the vastness of space created a sense of separation. Even as we understood that we were not physically central, we remained conceptually central. Our knowledge, our perspective, our interpretations formed the core of meaning. But now, meaning itself becomes less anchored. If systems exist that operate beyond our frameworks, then interpretation is no longer a closed loop. There may be processes unfolding that do not require human understanding to exist or to function. Reality continues. Indifferent to whether it is fully comprehended, this is not a loss. It is an expansion. Because within that realization lies a deeper form of curiosity. Not the curiosity that seeks to dominate, but the curiosity that seeks to belong. To understand not as an act of control, but as an act of alignment with a reality that is richer than expected. The scientific implications remain vast. New physics may emerge. New technologies may follow. Entire industries may be reshaped by discoveries that begin with these anomalies. But those are downstream effects. Upstream at the source is a shift in perspective. The universe is not only